Okay, I think it's time to start. So let's get going. Presentation today, modern data integration. So it'll be like 5 minutes of how the data integration as a problem kind of evolved over the years. And then basically 4 design patterns from that I've seen used more or less successfully in companies that are building data integration architecture like in the last, let's say, 2 years, something like that. So how do people who are modernizing everything are actually doing stuff, and what was successful and what is not so amazing. So about me, I'm working for Confluent. Confluent is a company that does Apache Kafka. We do a lot of Apache Kafka in the open source. We also have Confluent Platform, which is Apache Kafka plus other stuff we think you're going to need. I think a lot about how people use Kafka. I think a lot about how people do application architectures, how people build usable things from open source components, which seem to be kind of the defining problem of our time. I started out as a DBA, became a consultant, moved to engineering, and now I happen to be a product manager. It's kind of funny how you keep doing the exact same things with different titles, but that's another story. I'm on Twitter a lot, Strudel Gwen, if you want to talk about how you use Kafka. I'm always open to discuss architectures. It's something I like. I have a GitHub, and I'm going to show some examples throughout the discussion, and the examples are on my GitHub. So data integration and what happened to it. Well, when I started my career, I started it at year 2000. I said I'm ancient. And I started as a data warehouse DBA, basically. So working for a small company called HP. And we had, as a DBA running a data warehouse in HP, we had lots of problems. Data modeling was difficult. The whole problem of a data warehouse is that you're bringing in data from all around the organization, but you have to find a good common model, both for ingest and for reporting, and it's anytime someone was unhappy. Ingest was super, super difficult, right? You had an entire teams of Informatica and data stage people trying to figure out how to get data both fast, and then ingest has to happen overnight on those big batches, but if it runs over after 4 a.m., then the reports will be delayed and business people will start complaining. That was super difficult. Because of the way data was brought in and the integration happened between other teams, usually when one team had some data that they wanted in the data warehouse, it was a process of months just working with the teams and modeling and testing, and everything was very fragile, and we were always very scared to break something. So at any given time, you were 6 months away from actually having the data you want in order to build the report and make the decision you wanted, which was terrible. And then as we had more and more data in the organization, it became untenable to have it in a single database, and we had those huge Sun microsystem machines with thousands of CPUs, but huge NUMA problems. And then we tried Oracle Exadata, and that may work if you're HP, but it's super expensive, and it's also really, really hard to scale. And the whole thing still left us firmly in the low data between 10 p.m. and 4 a.m., run reports from 4 a.m. to 8 a.m., and the CTO gets the report at 8 a.m., and that's it. So it was just, the whole thing was totally untenable. And at some point, Hadoop showed up, and we moved to the data lake model. And the data lake model promised to solve the data modeling problem, first of all, because no more data modeling. You just throw the data in and hope it sticks. And we did that. And that solved a lot of issues for the people running the data warehouse, because no more data modeling. Ingest was super easy. Nobody could complain that the data is missing, because if it was missing, we just throw it in there. Throughput was fantastic. Batching was still a thing. And now there was a host of other problems, especially around data quality and how do you actually get the data and what do you do with it, and is it the data you need, and how do you clean it? That became really, really difficult. And now we are seeing transition from this data lake model to the streaming data integration model, where the data is represented by streams of events and is usually communicated between different services. Each of them owns its own database. So if you need a report, instead of going to the data lake and looking for all your data, you say, okay, I need some data from service A and some data for service B. I'll find myself talking to these services, looking for their events, and doing some kind of a stream of event-based data integration. And I'm going to talk, most of the talk is going to be about the data stream model and how does life look when you do data integration with the stream model, because that's how we see a lot of newer companies do things. One of the interesting things that happened during the entire transition is just that job titles kind of changed. When we were at the data warehouse and into the beginning of the data lake time, there was a lot of ETL engineers, the people who use the Informatica, DataStage, Talend, and Pentaho, all those things. And then at some point, I noticed that the people who were building the data pipelines, the one who asked me how to do data massaging, the guys I consult to, are no longer ETL engineers. They are just software engineers. And they don't really know Informatica, and they don't know DataStage, and they just write code in Python and Ruby and Java and all that kind of stuff. So something changed in between. In the beginning, I thought that this is probably because in the data lake, ETL engineers have almost nothing to do, right? They just dump the data over there and hope it sticks. On the other hand, the people who write applications that need to use the data have a lot of stuff to do because they are now responsible for stuff like data quality and the data model and how to parse it and how to manage it. Suddenly, all the responsibility shifted from the people who move data around to the people who are trying to use the data. So this kind of, I thought that this is why the jobs changed. But that's actually probably not true because pretty much all the jobs I was familiar with at year 2000 went away. So it's just part of a very big shift in the industry. The cloud took away some jobs, and then DevOps happened, and then test-driven engineering happened, and slowly but surely more and more things go away. And I think that this is why I'm asking who here is an engineer, and everyone raises their hand, and very few people will tell me, I'm QA, I'm a DBA, I'm a sysadmin. While maybe if I would do the exact same presentation here 8 years ago, probably you would be like half developers, half admins, and we can get you to fight each other because that's what we all do. Okay, and so the change from a data people to a software engineer changes a lot of things. And the main thing it changes is the goal. Engineers, more or less, what they do and what they're paid to do is to build an application that does something. And this is different from an ETL guy whose entire job is to get data from here to there and make some modifications for the data. It's not at all the same thing. And also the tools of the trade are different, right? As a software engineer, I know how to write Java and I know how to do Python. And I'm willing to learn some frameworks and some stuff, but I don't see a huge need for something like Informatica that does the point and click thing. It may be helpful. And I'm not averse to GUI, and I love my IntelliJ, for example. It's very helpful. But the tools that engineers use to build systems are very different than the tool that other people in the organization use to build things. So a lot of how we go about solving problems is just very different. I would also say that there's some creativity aspect to it, because you're not limited by if a tool can do it, I can do it, and if a tool doesn't do it, oh my God, what do I do now? You can actually have a lot more freedom around problem solving, finding your own patterns, figuring out what works. It also means a lot of responsibility. Now we have to figure out all the patterns and find out what works. So let's talk about those patterns, right? That was kind of the intro and motivation around the whole thing and how our world changed. Now let's talk about what do people actually do in this world. So the patterns I'm going to talk about is how everything is really a stream and what to do about it. Compatibility issues, because we are no longer in a data lake. We actually take responsibility for data being in the shapes that people expect it to be. Single message transformations and how awesomely they scale. And then data enrichment and how to make data, because data enrichment is usually the core of data pipelines. Taking events with some ideas and turning them into an actual facts about the world. So we'll talk a lot about how to do that in a streaming model. And throughout the whole thing, I'll use it as an example. A fictional large hotel chain, it's actually a combination of about 4 different companies that I've worked with throughout the years. So basically, they have hotel properties throughout the world and a website that you go to and you search for, I want a vacation in Hawaii at those dates, where can I stay, kind of thing. If you're not into hotels, I'm sure that Airbnb does something very, very similar. And I'm going to make a bold claim that all the data this organization and any organization has is really streams of events. You may choose to look at it in different ways, but it's all streams of events, and we gain capabilities by treating everything like streams of events. So examples for those events. First of all, we have our website, right? So page views are events. But page views are not just on the website. So if you use your mobile to look at different properties, those are also view events. So you have to take them into account too. If someone searches for something, my vacation in Hawaii, that's an event, right? Every search. If he clicks on something following the search, definitely an event. If he books something, if he gives you a credit card, maybe one event, maybe two events. If he shows up at the hotel and actually checks in, definitely an event. He goes to his room and swipe his key card to get in, you can bet that you going into a room is recorded. And the house cleaners that goes into a room and uses a different key to get in, it probably is also recorded, right? And then you go to the minibar and take out a drink. There is a sensor in there that checks that, hey, the weight is not the same weight anymore. That definitely gets recorded, right? They have to charge it to your credit card. This is like Internet of Things in action, and this has been around for a very long time. And then also things that happen to a database are events, right? So someone who is a customer with loyalty program and points goes in and changes his address or preferences, this is an event. If a property has to announce that, hey, we're under construction and few of the rooms are unavailable, this is an event. So everything is an event. And let's take a look at one of those, our page view events, because those are ubiquitous. No matter what you do, you have page view events. They look a bit like that. Page view events has a session ID because, cookies. They have a timestamp. They have a type of a view. This time you're viewing a property. So because it's a property, it also has a property ID. If you logged into the website, there's also your loyalty number ID. And also sometimes, how did you get in? So if I got an email with a promotion and I clicked on it, it shows that I showed up at looking at this property because of the promotion. That's how they know that the promotion was successful, et cetera, tons of metadata. And there is a lot of potential applications that can use this data, right? So if you go to Airbnb, for example, and you look at property, it will tell you 15 other people are also looking. And that kind of incentivizes you to book stuff, right? So they use those kind of page view events processed in real time to get this information. And then they can also make recommendations, right? People who search for Hawaiian vacations also booked those few properties. Promotional programs, things like if someone did X, then we want to send him emails about other opportunities, Y kind of thing. A/B testing, search relevance. Are people actually click on the results that are returned in a search? Affiliate programs. We pay bloggers to write about their amazing vacations in our hotel, and the links have a specific code. So if someone books vacation as a result of following a blogger link, the blogger will actually get money back. Super, super, super common in the industry and very valuable. All those things are driven off page view events. And the one thing that happens in the world where you have all those different applications, all passing events to each other, all trying to use the same things, each one of them has its own little database, is that you get a very, very messy architecture. And this is kind of simple, right? We only have like 5 web apps here and 2 large databases. This is nothing. Like real microservices have 300, old school SOA has 300. If you're microservices, you probably have 3,000 or 30,000, depending on how micro your microservices are. You probably have way more databases and stuff is way more messy and a lot more connections. But this is kind of the idea. Everyone talks to everyone and it's a mess, and every time you want another service, you have to figure out who you're talking to, all their APIs, and how to do it. It can get a lot simpler. So we say just put all the streams in Kafka. I'll talk about it in a second. It's well suited to manage streams of events, and we already agreed that everything is a stream of event. And then the apps will connect to Kafka to get their streams of events. And the basic architecture of Kafka, there's a lot of ways to look at Kafka, but the basic architecture is a collection of logs. And by logs, I don't mean like application log with text. I mean more like if you have a database, your database redo log or transaction log. Basically, it's an ordered collection of events. And when someone is writing his events, he just writes them to the next place, so it's a bit like a queue. And then readers can start reading the events. Usually they read them sequentially. So they start at a specific point and keep on forward. This is a super simple model, and there is two benefits in using actually three benefits in a super simple model. The first is that it actually models correctly pretty much every database in the world. They all have a write-ahead log. So it already is a good fit to the way people want to store data anyway. The second is that because it's very simple, we can optimize the hell out of the read and write passes. There are only two read and write passes that are very well understood. We can make it scale and perform really, really well, which we do. And the other thing is that because it's a simple model, a lot of people can understand it and use it. We have a lot of Kafka users in the world, and also contribute back. So Kafka is actually a super successful Apache project with a lot of contributors. Much of it is because the basic model is simple and people feel that they could actually work on it and make improvements. And that's something that I'm pretty proud of. So simple architectures have a lot of benefits. Now, it's not quite as simple because we need to scale. So we actually break it down in two ways. The first is that Kafka has multiple topics. A topic is more or less the equivalent of, let's say, a database table. So we expect all the events in the topic to be somehow related to each other and describe more or less the same thing. But then we take the log on the topic and we partition it. So each topic actually have multiple partitions. Each one of them is a log. And each one of them is ordered, but there is no order in between. And the reason we do it is plain and simple for scale. We can put each partition on its own disk or on its own machine. And if someone needs to read, maybe he doesn't need to read the whole thing. He can just read a single partition and have the data it needs. So it allows us to break down and parallelize a lot of problems. Going back to our Pageview events, let's dive into some examples of what people do with it. So a very, very, very common story is that, remember, the Pageview has, so just to be clear, I just realized I didn't clarify, storing the streams in Kafka is our first pattern. We're now diving into a second pattern. People have those Pageview events, they all have timestamp, and pretty much everyone who uses the event will need to use the timestamp one way or another, right? I mean, Pageviews from 3 years ago are just not as interested as the ones from today. So you have all those applications, and for example, if someone decides to store the event in a database, he will put it in a database with a timestamp that is usually modeled as a number. And if you have some kind of search optimization application, you read a timestamp and use it to generate a date object. Again, expecting number of milliseconds, and there is a constructor that uses it. But sometimes what happens is that someone says, I don't know if I like this whole thing with milliseconds since 1970. It's really hard to read when I'm kind of looking at it. Let's change it to a string. I mean, there are standards for strings. Everyone can parse strings. Let's just change it to strings. If he just goes ahead and does that, naturally, everything that tries to keep using those events will break. And I can't come close to tell you, like, it seems like I invented the example, but I keep running into this exact specific example all the time. And then I thought that it's just me being unlucky with the companies and teams I'm working with. But I went to Strata, and Uber did a great presentation about how they do the microservices in Uber. And they had the exact same story. Like, yeah, we had this JSON, and it has a timestamp, and someone, I think they changed it from a string to a long at some point. But the exact same thing happened to them. So it's not even just me. It happens to Uber as well. So what we really want is to basically keep compatibility, right? Make sure that people cannot just go ahead and break stuff later on. And I think it's something that people don't take seriously enough, because if you're building services, like microservices, service-oriented architecture, whatever you call it these days, if you know that you're building services that have to communicate with each other, you build good APIs, right? And you know that those APIs are a contract, right? So if you are building some kind of a REST service and you publish a REST API, you know that people will use it. And you know that if you change the smallest thing in the API, it may break other people's code. So what you really usually do, if you're responsible, is you build a lot of integration tests and automate deployment and do a lot of work to basically prevent anyone from accidentally breaking an API. And in Kafka itself, we have that. I think that a good percentage, maybe 20% of our system tests in Kafka are basically meant to validate compatibility, make sure that the protocol didn't change, that the public APIs didn't change. And we do it by running new versions against old versions. We have an entire framework to do that because those are contracts, right? And we're people who take our contracts seriously. We're not like presidents of the US, I'm sorry. Anyway, so if you're moving to the stream processing world where the communication, you still have all those services and applications that depend on each other, but now they communicate asynchronously, right? They write messages to an event stream and other applications read it, but it's the exact same thing. So they still communicate with each other. And in this world, the messages you have has some kind of a schema, right? It has what type is each field, which fields are there, what do they mean. All this information is your API. This is your contract. You write an event and other people expect an event that looks exactly like it or very close to being like it. And it's even worse than in the SOA microservices direct communication world because Kafka will store your events by default for a week, but you can configure it to be a lot longer. And then events usually get written to some kind of a database or a data store or data lake or whatever. So those events stick around for a really long time, and you may want to read them 3 years from now. So you really need to think about having new applications still being able to read old data, and also have old applications still being able to read new data because you don't know when people upgrade. So you have a lot of compatibility questions to figure out. And the key for keeping events compatible is, first of all, to decide what kind of compatibility you have. And this is completely agnostic to how you save your events, and you can use Avro, protobufs, or JSON, or whatever. But you need to understand, am I giving forward compatibility? If someone upgrades a service, if I upgrade my events to a new event type, and someone updates the database and adds a column, will the people who are reading data from database still be able to read all the events that didn't have this column? Or the other way around. Again, I'm updating my producer. I've added a few columns, but nobody updated, someone didn't update his consumer because it's hard to coordinate upgrades between large organizations, right? So I can upgrade my producer and it'll take 6 months for someone to upgrade the consumer. Will he be able to read it? So you need to think about it, and then you need to really codify the tests. So usually on your dev environment, you don't need to do too many checks, right? You just want to write some code, see that it works. But when you open a pull request or to Git, or you have nightly tests running in your CI environment, stuff like Jenkins, that kind of stuff, you really want to have something that validates that you didn't break compatibility. Just like you run unit tests and system tests and so on, you need to validate compatibility. And as your code kind of progresses on its way to production, you want to keep validating that nothing broke. And then in production, you really want a system that will reject schemas that are incompatible. If someone tries to write data to incompatible data to a topic, you want the guy who writes it to get the exception and not the other 10 guys who are reading it, right? I mean, it's better to cause it's a good principle in software engineering that you cause pain to the person responsible for the bug, right? If you can get that, that's kind of, it gets stuff fixed a lot faster. So we're trying to aim towards that. So those are the two places where you want verification. Obviously, catching stuff at the Git level means higher development velocity and a lot better all the way around. By the time code reaches production, it could be, if you're lucky, maybe an hour or two after the developer wrote it and it passed tests. But if you're not lucky, it can be 3 months later, 6 months later, maybe 2 years later. Well, life can be very difficult if now you have to deal with a bug that you wrote 2 years earlier. So Confluent, in part of our open source platform, has schema registries that kind of helps. It is currently somewhat married to Avro. We are trying to solve it and support other data formats with different compatibility stories. But the idea is that we have a Kafka topics that basically keeps all the schemas. And it shows up with a serializer and deserializer. And it shows up as a service, like very thin service, with a REST API. And this lets you do a bunch of stuff. First of all, if you use the serializer and deserializer, it means that it will check compatibility when you serialize and deserialize, which means when you're writing to Kafka, which means that events that are not compatible will get rejected before they make it into Kafka. That's fantastic in production. If you want to be more proactive, we have a Maven plugin that basically uses the REST API and takes a schema and calls validate, and will either pass or fail depending on compatibility. And that allows you to actually do the integration far earlier in your development cycle. Highly, highly recommended to do both. Whew. Okay, that was it on compatibility and why and how to maintain it. Now, ridiculously parallel single message processing. One of the important things to remember about Kafka is that it scales really well, and not in the Hadoop sense that you can have like 5,000 node Hadoop cluster. The funny thing about Kafka is that a single node, like a 3 node, because we want availability, 3 node cluster with nothing special, Amazon M3 mediums kind of thing, can pretty easily do 250,000 events a second. I'm talking about like 1K event, something like that. So a very small Kafka cluster will have really, really, really high throughput, like throughput that's kind of difficult to achieve in a lot of databases. And we don't want to lose it by basically having a single consumer that tries to handle all this and becoming the bottleneck. We want to keep parallelizing things later on. And in the grand tradition of MapReduce, if you don't need to reduce, if all you can do is map, if all you can do is have very small functions that can be executed independently by as many applications as instances as needed to process it, well, we can actually scale really, really well. So just as an example, suppose that our event has a credit card number. Page views typically will not, but who knows? Like booking may have a credit card number. And suppose that writing it into Kafka, we don't want the credit card number in there. For example, because we didn't do a PCI audit for Kafka yet, and we'll absolutely get fired for having a credit card number in there. So we need to start getting rid of those events, of part of the event, and we need to parallelize the processing. I just realized that I misspoke. The data in Kafka has the credit card number, per the example. Someone else down the line shouldn't have the credit card number. So I'm showing an example of getting rid of data on the way out of Kafka. It's consumer scaling that I'm talking about here. And the way we do that is that Kafka has a scalable consumption model. The idea is that you have consumers are part of a consumer group. If you use the message bus, there is always like topic versus queue, which I never remember. But in one model, if you have multiple consumers, they all get the events. While in the other model, if you have multiple consumers, each gets a share of the event, and together as a group, they all get the events. So Kafka allows both models. You can declare a consumer group. Each consumer group will get all the events. So if you have 2 consumer groups, A and B, reading from the same topic, consumer group A will get all the events, and consumer group B will get all the events. But if you drill down inside a consumer group, each consumer instance will only get part of the events. No less than a partition, so at the very least, they have to read an entire partition. But it could get, if you have 1 consumer, it will just get data from all the partitions. 2 of them, hopefully half and half. 3, you get it in thirds, and so on and so forth. So a very good way to scale things is simply by adding more and more partitions. Now, adding partitions after the fact can be challenging because we partition usually based on a hash of a key, And if you add more partitions, suddenly all the hash numbers change and things kind of start getting messy. So usually we want to create topics with sufficiently large number of partitions. And the way we usually do it is say, okay, consumers are usually the slowest part of the equation. Not always, but that's usually true. And let's look at the slowest consumer we have. Let's suppose that we have a consumer writing data to HDFS. It cannot possibly process more than something like 20 megabytes a second because that's how fast we write to HDFS. But we need a topic as a whole to do, let's say, 2 gigabytes per second. Well, 20 megabytes per second, 2 gigabytes per second, it looks like we're going to need about 100 partitions. Let's make it 200 just to be on the safe side and call it a day. So that's kind of how you figure it out. So you can see that the way to scale is by having more partitions and then having more consumers get data from the partition. And while you want most of the partitions to be in ahead of time, consumers you can add slowly. Maybe there's not that much data early on. You start with 2 consumers and you keep growing it as things are expected. If since we're doing data integration, it may be that your consumers would actually have a data store. Like our example, we're writing stuff to HDFS from Kafka. We have a nice system called Kafka Connect, which meant to make this easier. So basically, Kafka Connect is an API that allows plugging in connectors. And when you develop a connector, all you have to do is worry about how to integrate with either the data source or the data sink and not worry about the Kafka side of things because Connect will do it for you. And it has a lot of nice properties. It deals with a lot of stuff that's really hard to deal with normally, like fault tolerance and the schema management we talked about earlier. And the big thing is that it also includes simple transformations. So you can, in addition to plugging in a connector, you can actually plug in a lot of those transformations, like get rid of this field, mask the other field, change this, rewrite that, turn a JSON into CSV, turn something nested into a flat structure. A lot of those things that you need to do when moving data around is already built in. So that's pretty useful. And the big thing is that it just has a lot of stuff ready-made built in for a lot of the data systems you'll want to work with. And the way it works is that basically you have a bunch of Connect workers and you have those external databases lying around. And Kafka is somewhere off the picture. I don't show Kafka here. And you go and you make a REST call and say, hey, I need to get some data from those data sources. And it starts a connector. And the connector doesn't really get data, but it connects to those data sources and checks out how much data is in there. And it tries to decide how much we can parallelize it. And it starts a bunch of tasks based on that. So if we see that, hey, the log files are in 20 different directories, let's start 20 different tasks, each responsible for a directory kind of thing. And now the tasks go and start getting data from the data store, and the other end are writing it to Kafka, again, not show here. And if one of those fail, the task will be relocated by the framework as a cluster to another remaining worker. So you kind of get parallelism and failover 100% for free. Whew, okay, that was parallelizing stuff. Again, you can have consumers which can do ridiculously parallel stuff for you, or you can use Connect if there is data store on the other side, and it will do even a bit more for you. Now, let's imagine that we're doing a promotion. Our hotel has a new property that it wants to promote. And the way that a group in marketing decides to do it is that we'll find all the platinum members, those are our big customers and big spenders, who are looking at beach properties, and we'll send all of them email about the discount package in the new Hawaii hotel, hoping that they will decide to do their new vacation in Hawaii, in our new Hawaii hotel and not anywhere else. This means that we need data from a bunch of different places and then write data somewhere else. And this is an example for enriching events, right? Because our Pageview event, it has the session ID and timestamp and loyalty and property ID. But for us, we need, in order to make the decision on who gets the email, we need to know not just the loyalty ID, but whether or not he's platinum, and not just the property ID, but whether or not the property is on a beach. Properties usually don't move around all that often, I hope. Beaches may, because, global warming. Loyalty levels tend to change slightly more often. But in any case, we're trying to enrich with information that doesn't change a lot. So we're talking about, if you are from the data warehouse world, we're looking about a fact table. It's kind of like a fact table, right? The main stream of events with the page views, and then slowly changing dimensions about the properties and the locations and different loyalty ID levels. And your basic architecture will probably look a bit like that. Page view events should land in Kafka. We have a consumer reading them. It has to do some kind of enrichment. It has to get a decision. Maybe it's writing the decision to something like Elastic, so people can later figure out whether it did a good job or not. And then it also needs to produce an event that says, hey, please send an email, that a send email service will later read. So this whole thing on the right side, is the stream processing application. We know it's a stream processing application because it reads data from Kafka, it does stuff with it, and it writes data to Kafka. That's what stream processing applications tend to do. And people talk a lot about how stream processing can be really complicated, and it can be really complicated, but at the core, it can also be very simple. We read a stream of events, we do something to it, and we write a stream of events. So that's why I think that all data integration is stream processing. You always read a stream of, unless you do it really batchy once a day, you always read events and process them and write events somewhere else. So this is the basic architecture. And we're focusing on the enrich part. And in order to get the property locations and the loyalty levels and all those, well, we got an event that has an ID. The simplest thing that comes to mind is to take the ID, go to a database or maybe another service, and say, give me the location and platinum level of this for those IDs. And that's actually surprisingly common. Like everyone does that, especially with services. Nobody feels comfortable querying a database directly from their Kafka application. I've seen people do it, but then they ask me like, hey, do you think it's okay? And I'm like, no, I don't think it's okay. But they actually do REST calls without even thinking about it twice. No matter how you do it, there are still some problems. Latency, right? It's like maybe 50, 100 milliseconds getting to a database and back. Throughput, right? Our consumer or Kafka application may be capable of doing 250,000 events a second. Your database can probably do 1/10 of that, maybe 1% of that, maybe. So you're kind of at a risk of DDoSing your own database. And your DBA, if it still exists in your organization, will absolutely hate you forever if you do it. And then there's also an availability question. If you go to one service or two, it's not a big deal. But I've seen a lot of apps that enrich by contacting maybe 20 different services. The probability of any one of those being down or busy is actually pretty high. So how do you do retries, right? And where do you store the messages while you're retrying? It gets really, really complicated. So what we're doing at the fundamental level is that we're trying to join a stream of events to a table, right? And we're doing it by going to the table directly. But there is a better way to do it. So the first improvement is that we need a cache, basically, right? Every time you have a latency, throughput, and the DBA may kill me problem, you always put a cache. That's like our first line of defense. No, I'm not killing your database. Here is my... So you have a cache, but obviously a cache brings with it its own set of problems, mainly the question of how do we keep the cache up to date. If we start expiring stuff out of it too often, the cache is useless. If you don't expire data at all, it becomes stale, and we kind of have to find a happy medium, which turns out doesn't exist. What we actually want is to update the cache every time an event happens, right? If someone gets to the new loyalty level, you want to update the cache immediately. And this is actually possible to do it if you do it the correct way. So the little circle in the application is the application's local cache or local state. That's the local copy of the loyalty table as belongs to the application. And now our application, in addition to consuming events about page views, wants to also consume events about the loyalty levels. And every time a loyalty level changes or you have a new customer and you have to know about if he signed up to the loyalty program and so on, it gets an update. and it gets the update as an event, it updates its local cache, and it can use its local cache to do this kind of join. And that's pretty easy. The only question is, how do we get updates out of the database? The question of how do we get updates of the database is a question that goes all the way back to the data warehouse world, where we still needed to get updates out of a database. And it's called a change data capture. Basically, get an update every time the database changes something. Usually it's done by listening to the database changelog. Like SQL Server has some views that do it, and every database has its own way. Kafka Connect has a pretty nice collection of connectors for various databases that all do this kind of stuff. So there's the Debezium project that does it for MySQL, Postgres, and Mongo. Someone out there is using to do it to Cassandra. Golden Gate is the obvious choice of doing it to Oracle, but there is also DBVisit if you're a bit on the cheap side like me. As far as I know, nobody does it to Oracle for free yet, but it'll be nice if someone did. So basically you build this kind of system, you get changes out of the database, basically this update happened, this insert happens, and you put it in your application. So using Connect, you take a state, right? Database holds the state of the world at any particular time. You turn it into a stream of events, update, insert, and then you take the update, insert, the stream of events, and turn it into another state, this time inside the application. So maybe that's a better way to look at it. If you look at database, if you run select star, you see the state of the table as it is right now. If you look at the database log or at the change log in Kafka after you captured it, you see kind of all these changes that happened. That's the entire history. If you look back enough, you can see you recover all the database in its only various states. That's how point-in-time recovery for databases actually work. And then because you can do it, you can start applying those changes to another application in the cache and get the same state of the table continuously updated. That's really, really cool, and that's something that I see a lot of people do and super useful. The only problem is that it's not trivial to do, because you have to maintain a distributed cache, and you really want to also persist the state, because in our experience, rebuilding the state from Kafka history, even though Kafka has low compaction and a lot of features that make it a bit better, it's still quite significant. It can basically slow down the application start time by multiple minutes. And then also things like co-partitioning, because you're doing a join, you need all the events for specific user IDs to be in the server with all the state for those specific users. So it gets kind of difficult. Kafka streams and its good friend Samza make it a lot easier. They basically have constructs that do this exact thing for you. Please build me a table out of a topic, and then please join this stream with the other table. And you can see we have an entire blog post on exactly how you do it and when we do it and how it works behind the scenes. And it has the complete example. I think the example there is you have a table with regions and you have Wikipedia edits and you want to know which region is more active on Wikipedia kind of thing. So yeah, if you use something like Spark Streaming, maybe they also have a way of making it easier. I honestly don't know. As I mentioned someone this morning, my Spark Streaming knowledge is about 3 years old, as I probably advanced a lot from then. Okay, we go to the bonus content, and we have 15 minutes, so I will get to do the bonus content. Yay. So that was joining a stream to a table, which is not that hard. I mean, it was hard, we needed to do some work, but it's actually not as hard as joining 2 streams. Why is joining 2 streams harder? Because a table is a state. You can compact it, right? You get all those updates, but at the end, they only apply to that many keys. You pretty much know how much space it's going to take, like how many Sheraton customers are there in the world? Let's say 30 million. That's it, right? You know exactly how many. Let's put it on 30 machines, 1 million per machine. We need 1 megabyte space for the cache. It gets pretty easy. Streams are unbounded by definition. They are really, really, really large, and they get larger. So joining them is kind of a more complex problem, even conceptually. Like, what does joining streams even mean? So let's look at an example. Our same hotel chain wants to do search relevance. which means that a user searched for, I want a hotel in Philadelphia, and we show a bunch of results. We pretty much want something like 80% of the users to click the first result because that's the best hotel in Philadelphia, maybe 15% clicking the second result because that's an okay hotel but not that nice, and then maybe the rest of the page gets everyone else. We don't really want users to keep moving between pages and looking for a hotel. We want our result to be relevant. In reality, whether or not it happens, who knows, right? We need to find out. So we have the Pageview Events, people viewed properties, and we have the search event, and we know who searched, we know when they searched, and we know what they searched for. So, and both of them are streams, right? You can't compact either of them. So you end up with two large streams of events, and you need to join them somehow in order to know, basically, that this search in this stream of events caused the other view in the other stream of events. We need to establish some kind of causality between those two things, so we need to join them. And it turns out that the way to do it is by a window join. Basically, if the click happened within maybe 10 seconds of the search, we think that they're related. If it happens half an hour later, probably a totally unrelated click. So we keep this window of time on each of those streams. We turn each of those windows into a hash table, right? User and clicks kind of thing. And then we join them. And we match them to each other and see that if every search matches to a click, we can basically then output the results. And we keep doing that, right? Those windows just keep moving forward. So basically, you do kind of a window join on two streams and have a third stream of output results. All of it is kind of windowed and moving forward continuously. And it should be obvious that time is very, very important here, right? Like our whole conjecture is that the click is relevant to a search if it happens within a certain window of time. So it behooves us to be really, really good about our timekeeping. And this is another one of those things that turn out to be harder than expected. When do events even event? Like, when I say that a page view has a timestamp, that's the time that the page started loading in a browser, the time the page ended loading in a browser, the time that the web app decided to create the event, the time that the producer decided to try and send the event to Kafka, and Kafka may be down for half an hour, and who knows, the time that Kafka got the event, or even worse, what if it's actually the time that our stream processing application got the event, and who knows when did that happen, and if someone had to restart the application and everything changes. So there's a lot of places to decide on time. You'll be surprised how many stream processing applications basically think that the time that they're looking at the event is the time that the event happened. So if because I'm a stream processing application, I run continuously. If I go the event now, the event happened now. If I get the event 5 minutes later, clearly it happened 5 minutes later. That's not the way things work. So we'd rather that when you develop software that produces events, you will actually put a timestamp that is meaningful to your application in the event itself, right? So if you're a sensor in a hotel room when someone passes the key, probably the time should be recorded on the sensor in the hotel room, no matter how many jumps the event has to do on the way, getting to a REST proxy, and from the REST proxy to Kafka, and from there to a consumer, whatever. It has to do a bunch of things in the way. You want it to always be the time that the person actually did something on the door. So you want it to be meaningful for the application. If you completely fail to do it, new versions of Kafka will actually timestamp the event itself by the producer when the producer sends it. It may be too late, but hopefully not too much too late. If you fail to do that, I guess I'm running late. If you fail to do that, Kafka will timestamp the event for you, so you'll get a time in Kafka. That's not that amazing, but at least it's a single time for an event. It will never get another time. You never want to be at a place where your consumer actually looks at the time on his machine and does something. And then using that, it's obviously clear that sometimes events arrive really late, especially if it's from a hotel room. I mean, you know what hotel Wi-Fis are like, right? I mean, the event can be like 3 days late. Happens quite a bit. So we really need to be able to take the update and not put it in his own time window, in the time windows that you're computing right now, because it's a late event. It showed up at the wrong time, and putting it in the time windows that you're merging this second will absolutely be the wrong thing to do. You need to actually update a previous time window that you may have created half an hour ago, and just say, hey, the click happened 3 days ago, but we just got it now. Can you please update that this search got this click anyway? And if the buffer still exists in memory or the database or something else, you could actually update it and generate a new result, put it on the stream of results. Now it's its own late result. Oop, we have an update on something that happened. But if it gets written to Elastic, well, Elastic will just get the correct data 2 days later. That's kind of the magic of streams. Data continuously arrives, the results are continuously updated. You can only get more certainty that things are true, but you can never be 100% certain that everything is true. That's correct for life in general. So again, it's kind of hard to implement in reality. You have to have 2 buffers, you need the state, failover, recovery, keeping those windows for a certain amount of time. Again, Kafka streams have a small construct that makes it easy. And this specific event of enriching a click stream with searches is on my GitHub, so you can go and just look at how I did it and tell me I'm doing it wrong. It seems fairly common on GitHub. By the way, I know I'm doing it wrong and it's not my fault. The Kafka Streams API is still evolving. So if you show up and it doesn't compile at all, it's probably because they changed the API on me again, and let me know and I'll figure it out. Okay, recapping. You want to do everything as a stream, and it helps to keep them all in one place, maybe Kafka. You want to make sure the data is compatible, so one change will not blow up everything else. Ridiculously simple message transformations that only touch a single event are ridiculously parallelizable. And you can do cool stuff to enrich events by optimizing the joins of different streams or streams and tables. I hope you learned something useful. If you like Kafka, by the way, we have Kafka in New York City, which rumors are is a short train ride away. So it's actually a day trip for you guys. May 8th, and there is a discount code. That's a really, really good discount code, and I have to talk marketing into letting me show you guys that. So definitely use it. And if I wasn't feeling interested in Kafka, I totally wouldn't miss it. We have Tom Crayford from Heroku talking about how he ran Kafka at huge scale. We have New York Times talking about using Kafka as a source of truth, which I'm super excited about. These guys know what they're saying. And yeah, anyway, a lot of really nice examples. We have like Goldman Sachs talking about how to make Kafka really, really reliable for financials. So yeah, anyway, that'll be really cool. Whew, I'm done, and we have a few minutes for questions. Yes. You have to wait for a nice lady with a microphone.
On the topic of event schemas, you mentioned that the workflow of the event schema can be challenging. So wondering, what is the workflow of the event schema? Like who decides the change is going to happen, and then how do you implement the change between the consumer and the producer? Oh,
okay. That depends on the organization a lot. I mean, some organizations have a lot of process for schemas, and usually they have a lot of process for everything, and there's like this team that you have to apply for a schema change, and they have a 2-month process and a committee to approve it. And then some companies are like, hey, the developer can do whatever the hell he wants. Usually in that scenario, the producers are the ones who have the power to change the schema because they create the events. And then just as I said, I don't want to put a lot of process onto people who didn't have it before. I don't want to slow engineers down. And that's why I'm like, hey, we have a Maven plugin, put it in your continuous integration with the tests, and they'll simply get an error if they broke something. And if it didn't break anything, great, it's compatible, and they can do it. So, I mean, why generate process if you don't need to?
Hi, thank you. Will Kafka Stream support broadcast joins?
I think if it doesn't already, then it will in the next release. We call it global K-table joins because I'm not responsible for the names, and clearly they don't know databases. But yeah, look up global K-table join. Either it already exists in Kafka 0.10.2, or it will be in 0.11. I have a hard time keeping track. There was a question up here.
I was wondering how Kafka interacts with, say, database consistency levels. So if I'm only getting guaranteed ordering on a partition basis, then if I have stronger consistency at sort of the producer side, do I lose some of that?
Okay, there is no easy answer. I can say that you don't lose any more consistency than you would by querying the database with the ID after the fact, in which case there is absolutely no guarantee that what you are seeing when you query has anything to do with what happened when the event was there. Yeah, you do, a lot of people do a lot of good work to reconstruct consistency. So they have the connector, because if you look at the change log in the database itself, the redo log, it does have all the commit messages. So you can actually say which changes belong to which commit. And a lot of people do a lot of work to reconstruct things correctly at the other end. Whether any of it is super popular, useful, and works out of the box right now, I don't think so. So it's one of the things that are kind of still slowly evolving. If you show up at Kafka Summit, there is a talk about change data capture in databases specifically, and I think that's one of the things that's going to get covered.
Thank you. Do you have suggestions for resources for common design patterns for architecting solutions using the kind of asynchronous event-driven model as opposed to REST API, for example, a big fat REST API
so
stack?
It's not exactly Kafka specific, but first of all, Confluent has some talks about microservices, and it's called the data dichotomy, and kind of how to exactly move from services talking to each other to more asynchronous models. So that's, I would look at, there's a blog post, and there's like 2 talks, and there should be a third one coming up. When I was learning how to do it, I basically read a domain-driven design book and find that most of it applies actually quite nicely. And then, yeah, I think that Lightband has various reactive, how to move from monolith to microservices and a lot of the reactive models. And I think that those were pretty useful to me as well. So I can't we didn't write the definitive guide, but those are the resources that come to mind when I was working on doing the same thing. Okay, I think we're good. Thank you, everyone.